Hey there, Math 186 friends. Finishing up Chapter 8 here. Just a reminder what we talked about last time in 8.5, trig forms of a complex number. So we can do really cool stuff with complex numbers if we put them in trigonometric form. So just a reminder, if we have a complex number of the form a plus bi, we can plot it in our complex plane. So even though this looks like our xy axis, it's really a different entity going on here. It's a real axis and the imaginary axis. So we go either right or left a units. If a is positive, we're going to go to the right on the real axis. If a is negative, we'll go to the left. And then b, we're either going to go up or down. So just let's say a is here, and let's suppose b is here. This would represent the number z in the complex plane. And once we have this number plotted, we can get some features from it. So the distance that the point falls, the complex number falls from the origin, is called the modulus. And this angle that it forms from the positive x-axis is called the argument. So we have z equals, in its complex form, r times the cosine of theta plus I sine of theta. And we often write it in the equivalent trigonometric form so we can do some cool stuff with it. So we'll see that in a minute. R is called the modulus, or the absolute value. And theta is called the argument. So just as a refresher, let's throw the number square root of 3 plus I into its equivalent trigonometric form. So square root of 3 is about right here. I, the coefficient here is 1, that we don't see. We're going to go up 1, square root of 3, so this would be the number right here. So I like to think about my right triangle trigonometry. If this is 1, this is the square root of 3. I can use Pythagorean's theorem. 1 squared plus the square root of 3 squared is 4. Square root of 4 is 2. So I recognize this is one of my basic triangles. This is a 1, 2 square root of 3 triangle. And I know that this angle is 30 degrees. So therefore, we can write z in its equivalent form, 2 times the cosine of 30 degrees plus I sine of 30 degrees. Now, don't forget, this is where we stop, or we can write it if we want to use radians. Again, just follow the directions. If it doesn't tell you to use degrees or radians, then either one is fine. Pi over 6 is equivalent to 30 degrees, so sine of pi over 6, right? So this is an alternate way to write the square root of 3 plus I. If you actually calculated the cosine of 30 degrees, it'd be the square root of 3 over 2. 2 times the square root of 3 over 2 would be the square root of 3. Sine of 30 degrees is 1/2. So I times 1/2 times 2 would give me just the single I. So hopefully you got a chance to look at some of that stuff. We also talked about last time, given a complex number, in its trigonometric form, we can add and multiply, or no, what we did multiply and we did multiplying. And we can multiply two complex numbers in their equivalent trigonometric form by multiplying their absolute values or their moduli. And then we take the cosine and we can just add those two angles together. Theta 1, the argument from first complex number, plus the argument from the second complex number, I sine theta 1 plus theta 2. And just a reminder, we could write this like this. We can write cis theta 1 plus theta 2. Cis is just shorthand for cosine of theta 1 plus theta 2 plus I sine. So this right here just means this. I don't tend to use that. I just never have, but you are welcome to. And if we want to find the quotient of complex numbers, well, it is the modulus from the first one, whatever that, the complex number in the numerator, over the complex number in the denominator. It's going to be the cosine of the argument of the numerator complex number minus the argument of the complex number in the denominator, plus I, and then the sine of the difference, the same difference. So we did a couple of examples of that last time. Right, so that ended, that's what we talked about in 8.5. 8.6 just adds a couple twists on this. So 8.6 is called De Moivre's theorem. So De Moivre's theorem says if p is any positive number, then a complex number to the power, well, we put the complex number in its equivalent trigonometric form, and then we can just raise the modulus to that power, and we can multiply the angles to that power. So keeping in mind a plus bi has to be put in its trig form to use this. So let's suppose I wanted to find the square root of 3 plus I to the 9th power. Now you could sit here and write the square root of 3 plus I times the square root of 3 plus I times the square root of 3 plus I 9 times. But De Moivre's theorem, and that the proof is in the book, I believe it's a proof by induction, says, hey, we have this cool little template. Here we have z to a power. The first thing you have to do, though, is write z in its equivalent trigonometric form. Well, we just did that on the first page here. So 3 plus I can be written as 2 times the cosine of 30 degrees plus I sine 30 degrees. And you can do this in radians or degrees, whatever suits your fancy. So now, according to De Moivre's theorem, if we raise z to the 9th power, it says that's equivalent to raising the modulus to the 9th power times the cosine. Well, 30 times 9 is 270 degrees plus I sine of 270 degrees, right? And we got the 270 degrees here and here because 30 degrees times 9. P was 9, right? And this was my argument. So 30 times 9. All right, now we started with a complex number in its standard form, so we want to answer in a standard form. So now we have to find the cosine and the sine of 270 degrees and 2 to the 9th. And if you do 2 to the 9th on your calculator, I believe I did this right. This is going to be 512. All right, well, 270 degrees is an angle that lands on the negative y-axis, and any angle who lands terminal side on the negative y-axis, the cosine is 0, and the sine would be -1. So therefore, square root of 3 plus I to the 9th power, well, 0 just cancels out, is going to be -512I. So if you literally multiplied this out, square root of 3 plus I times the square root of 3 plus I times the square root of 3, and just kept doing it in chunks, it would all reduce down to -512I. Cool little theorem. An extension on De Moivre's theorem is called the nth root theorem. Suppose I wanted to take the square root of a complex number or the cube root of a complex number. I wanted to square root this whole thing. Well, we have a template for that too. The proof of this, I believe, is in your book. If not, you can Google it. If it's something that you want to talk about, I would be happy to talk about it. So the nth root theorem says let n be any positive integer, so square root, cube root, 4th root, 5th root. So the roots can be found by taking the nth root of the modulus times the cosine. You ready for this? This gets a little tricky. The argument divided by n plus 360 k divided by n. Let me write it all down and we'll talk about it. Plus I sine theta over n plus 360k all over n for k equals 0, 1, 2, and you go up to 1 less than the root. So if we're taking the 10th root, we would go from 0 to 9. If we're taking the square root, we would just go from 0 to 1. So I'm just going to write this down, and we're going to do an example because I think it's a lot easier to do an example than to talk through this. So where z is the complex number written in its trigonometric form. All right, so let's start with an easy one, finding the square roots of a complex number. this guy up. All right, so to find the square roots of a complex number. So square roots, we are looking for the square roots of z, which according to this template is, well, we have to put this in its equivalent trigonometric form, -4 plus 4 square root of 3i. Need trig form. So I think to save on time, I'm going to tell you what the trigonometric form of this number is. Note, -4 plus 4 square root of 3i is equivalent to 8 times the cosine of 120 degrees plus I sine of 120 degrees. So put that angle in standard form. You'll see that it's going to fall over here. -4 square root of 3 is going to be over here. You're finding this angle and the distance from that point to the origin. And this is what you're going to get. So if you're struggling, so to do, make sure you can get from this point to this one. And if you're struggling, by all means, zoom in on me. So the square root of z is going to be the square root of 8 times, I'm looking at this template right here, so n is 8, I'm sorry, n is 2, it's the square root, 8 is the modulus, so it's going to be 100 and the cosine of 120 degrees divided by 2 plus 360k divided by 2 right there. All right, so I know this is a lot more horrible than it looks. No, I'm sorry, it looks a lot more horrible than what it is. It's not what I mean. All right, so let's keep going. Square root of 8 times the cosine of 120 degrees divided by 2 is 60 degrees plus 180 degrees k plus I sine of 60 degrees plus 180 degrees k. So we just divide the argument by the root we're looking for, and we divide 360 by the root that we're looking for. All right, now what does this all mean? Well, k, if you look back up here, it says go k, start with 0 and end with 1 less than the root. So if n is 2, we're only going up to 0 and 1. So this is for k equals 0 and 1. So if k equals 0, we're going to get our first root, which would be the square root of 8 times the cosine. Well, if k is 0, this term disappears and it's just 60 degrees. So it's 60 degrees plus I sine of 60 degrees. Now remember, we started with a complex number in standard form, so we want to write our answer in standard form. So this is going to be the square root of 8. Cosine of 60 degrees is 60 degrees would be 1/2. Plus I sine of 60 degrees would be the square root of 3 over 2. Now we're going to clean this up because we don't leave the square root of 8. The square root of 8 is equivalent to 2 square root of 2 times 1/2 plus I square root of 3 over 2. All right. So let's keep going here. So 2 square root of 2 times 1/2 is the square root of 2. 2 square root of 2 times I square root of 3 over 2. Well, the 2's cancel. Square root of 2 times the square root of 3 would be the square root of 6. So that's my first root. That's my first square root. And my second one would be, if I let k equal 1, then I would have the square root of 8 times the cosine of 60 degrees plus just 180. Woo, let me slide that down. Let's go back to that template right there. So we're going to add 180 one time. If we add 180 twice, we would be back at an angle that's coterminal with 60 degrees. So that's why we stop at 1. So plus 180 plus I sine of 60 degrees plus 180. All right, now we got to clean this up. Square root of 8, I already know is 2 square root of 2. And we're going to have the cosine of 240 degrees plus I sine of 240 degrees. And it's often going to ask you this for exact values, so we don't want to just be popping these in our calculator. 2 square root of 2, cosine of 240. Well, 240 is in the third quadrant with reference angle 60 degrees, but the cosine in the third quadrant is negative, so negative 1/2 plus I. Sine is also negative in the third quadrant. So we do the distribution, and we are going to get negative square root of 2 minus I square root of 6. So that was the second square root. So therefore, complex square roots of negative 4 plus 4 square root of 3I are square root of 2 plus I square root of 6 and negative square root of 2 minus I square root of 6. All right, so it's pretty easy when k is 2. I'm sorry, when we're taking the square root and k only goes from 0 to 1, doesn't exceed 2. So I'm going to set up the next one, but you're not going to be asked to find the details of all of this, but I just want you to see how it works. So let's find the 6th roots of square root of 3 plus I. Right. Well, we already know, let me see, the square root of 3 plus I is, we already did this guy, didn't we? Square root of 3 plus I. And I swear I wrote that down. We just did this one, didn't we? We just put this guy in standard form, square root of 3 plus I. Right here, this is it. So square root of 3 plus I would be, so we have to write it in z equals 2 times the cosine of 30 plus I sine of 30 degrees. So therefore, the 6th roots, right? We're going to do the 6th roots of z are going to be the 6th roots of 2 times the cosine of 30 degrees over 6 plus 360 over 6k plus I sine of 30 degrees over 6 plus 360 over 6k. So we're going to now, let's clean this up a little bit. 6th root of 2, can't do much with that guy. This is going to be the cosine of 5 degrees plus 60k plus I sine of 5 degrees plus 60k. Again, I'm going to leave these in their equivalent trigonometric forms because they're not going to be pretty, but we'll talk about it when we get there. So if k equals 0, so we always start with the 0 one, and that's going to wipe out this little piece right here. So the first of the 6th roots would be 6th root of 2 cosine of 5 degrees plus I sine of 5 degrees. 5 degrees. These would cancel out if k is 0. If k is 1. Now 5 degrees we'd have to use some of our combinations of our tricks from previous sections, maybe, you know, half angle, double angle formula, sums or differences. So this would get quite ugly to hash out, but I'm just doing it for the process. So the second one would be, so now I just look at this, and this is what we're going to keep adding to the previous one, 60 degrees each time. So it's going to be the 6th root of 2 times the cosine of 65 degrees plus I sine of 65 degrees. And when k is 2, and because we're taking the 6th root, we're going to go up to k equals 5. So the 6th root of 2, we add another 60 degrees, so the cosine of 125 degrees plus I sine 125 degrees. Not pretty answers if we were to try to write them out back into their standard form, so we're just going to leave them in the equivalent trigonometric form. The 4th root would be the cosine of 185 degrees plus I sine of 185 degrees. The 4th one would be the 6th root of 2. Cosine of another 60 degrees would be 245 degrees plus I sine of 245 degrees. And then the last root would be the 6th root of 2 times the cosine, add 60 degrees, we're at 305 degrees, plus I sine of 305 degrees. Now notice if we added another 60, we would be at 365 degrees, which would be coterminal with 5 degrees. So we would be right back where we started. So these are the 6th roots of the square root of 3 plus I, all in trigonometric form, because none of these are nice angles, so I'm not going to take the time to do all the work, because literally it would be hours doing this. But at least you saw the process. Right, to do. This is again our last section in 8.6. So to do, read 8.6. So there's 3 sections in 8.6, and there's going to be 3 sections in chapter 11. And that's what will make up your 3rd test. So 7 to 21 odd, 33 and 35. Alex, you can now do whatever chapter 8 topics you have. It's not all of chapter 8 topics, and you have 38% plus or 5+ hours due on Wednesday 4/15. Is that what it would be? Yep, 13/4/15. All right, guys. Have a good day. See you later.